if T is a linear transformation from a vector space V to a vector space W, it might happen that two different elements of V get mapped to the same element of W. Or it might be the case that that never happens. If it never happens, the linear transformation is called injective. Let's look at this property a little bit. So let's let V and W be vector spaces. And let's suppose we have elements V1 and V2 that are different in the vector space V. Some linear transformations might satisfy T of V1 equals T of V2, while others satisfy T of V1 is not equal to T of V2. There's no rule about linear maps that say that they have to map distinct elements of V to distinct elements of W. It could happen both ways. So no rule about linear maps require distinct elements of V to be mapped to distinct elements of W. So for example, let's let V K be the space of polynomials of degree less than or equal to K. And let's let T1 from V3 to V2 be differentiation. So P of X gets mapped to P prime of X. Then T1 of 1 minus x plus 4x squared equals, the constant differentiates to 0, negative x differentiates to minus 1, and 4x squared differentiates to 8x. And T1 of 2 minus x plus 4x squared differentiates to, the constant goes to 0, and we've got minus 1 plus 8x again. So these two different polynomials have the same derivative. That's something that you know since calculus. So it's possible that a linear transformation takes two different elements and sends them to the same element. Now let's let T2 be the map from V2 to V3 that sends P of X to X times P of X. So T2 of A naught plus A1x plus A2x squared equals A naught x plus A1x squared plus A2x cubed. So let's suppose that T2 of some other polynomial, B naught plus B1x plus B2x squared equals A naught x plus A1x squared plus A2x cubed. Well, the way the map works, the coefficients are just going to stay the same and end up next to higher powers of x. So if this is true, then we must have b naught equals a naught, b1 equals a1, and b2 equals a2. That is b naught plus b1x plus b2x squared equals a naught plus a1x plus a2x squared. So with this map, if we get the same element of w, w being v3 now, then we must have started with the same element of v, which is v2. Distinct elements are going to get mapped to distinct elements. So we call a map injective if it's like the second one. So you call a linear map T from V to W injective if V1 being different from V2 in V implies that T of V1 is different from T of V2 in W. So we say that T is injective. We also say that T maps V into W. Because if the different elements of V get mapped to different elements of W, it's sort of like we have another copy of V sitting inside of W. Now, in case two ways to say the same fact isn't enough, we have a third way that people say this. We also say that T is 1 to 1. So every one element of V gets mapped to one element of W. We can't have two different elements of V that get mapped to one element of W. That would be 2 to 1. A 1-to-1 map doesn't do that. So three ways of saying the same thing. T is injective, T maps V into W, or T is 1 to 1. Now every linear map can be represented as left multiplication by a matrix once we choose a basis of the first vector space and a basis of the second vector space. So let's say we fix bases B and C of the vector spaces V and W. And let's let A be the matrix of T with respect to these bases. So there's a nice property of A that tells you if the map is injective. T is injective if and only if the null space of A is just the zero space. So the reason is this says that T is injective if and only if the kernel is the zero space. Kernel of T is the same as the null space of its matrix. So let's suppose that the kernel is not zero. So it's not the zero space. Then there is some element v in the vector space V not equal to 0, such that T of V equals the zero element of W. So the kernel is all the things that get mapped to 0. So we've got something besides 0 in the kernel. We've got this element V in the kernel that get mapped to 0. But then V, which is not 0, and 0 satisfy T of V equals T of 0. Now if we two different elements that get mapped to the same place, then that means our map is not injective. Alright, so that proves that if the kernel is not 0, then T is not injective. Or I guess you could say, if T is injective, then the kernel is 0. So now let's suppose that T is not injective and see if we conclude that the kernel is not 0. So suppose T is not injective. So that means that there are two elements, let's say U and V in the vector space V, which are not equal, but T maps them to the same place. T of U equals T of V. If that happens, then we have T of U minus V equals T of U minus T of V because T is linear. And if T of U and T of V are the same thing, then I guess this is 0. But U minus V is not 0, since U and V are supposed to be different. So that means that we have something in the kernel. We have something that mapped to 0 besides 0. So that means that the kernel of T is not just the 0 vector. And if the kernel of T is not just the 0 vector, and the coordinate version of kernel of T is null space of A, that means that the null space, well, in this case the null space is not 0, but the kernel of T is 0 if and only if the null space is 0. So this was T not injective. If T is injective, then the null space of A is 0. The end.